Just to make life more interesting, we talked about climate sensitivity as not accounting for carbon cycle feedbacks, and we said carbon cycle feedback has concentration carbon feedback and climate carbon feedback. Now we will add additional complexity that actually the carbon cycle sensitivity to climate change is not constant in time. If you look at past periods and the current period, and obviously which means going into the future, the sensitivity of the carbon cycle itself is going to depend on the background mean climate or the climatology in which things are happening. Medieval warm period versus the transient warming we are in now versus the little ice age, and so on and so forth. So this is a model exercise using a model called Community Earth System Model from NCAR, National Center for Atmospheric Research in Boulder, Colorado, which has been a pioneer in many climate modeling and ocean modeling, atmosphere modeling, and so on, and now also in Earth system modeling. So I won't go into the details again, but just definitely want to give you a sense of the frequency of the carbon cycle sensitivity over different periods. So you can see that the ranges of climate carbon cycle sensitivity in terms of ppm per degree C warming. So if you warm 1 degree centigrade, how much additional CO2 would be perturbed, released into the atmosphere, or fluxing in and out of the atmosphere, ocean, and land, and so on. So here you have the common eras of 1300 to 1500. So this was just the end of the medieval warming and the beginning of the Little Ice Age. By 1500, Little Ice Age was already manifest in Netherlands and many parts of Europe, including UK and so on. 1150 to 1350 common era shows there was a lot of volcanic eruptions around the beginning of this period, and this has overlapping period with this, but you can see that they are still able to be separated in the model based on solar forcing. Remember, we looked at the various sunspot minima during this whole period, which actually led to lower solar output and facilitated the Little Ice Age, which presumably could have triggered the end of the medieval warming, which led to, for example, the demise of the Vikings who had settled Greenland, which around this time probably was initiated by enhanced volcanic activity and the cooling. Okay, 850 to 1500 common era. So that's getting more into the overlapping periods over the whole medieval warming and Little Ice Age. This is the control run, which is kind of the pre-industrial simulation, and this is 850 to 1050 C. I won't go into the details of why these kind of overlapping periods were picked. So they have all overlapping 50-year periods here, as you can see in the caption. But nonetheless, when you look at a longer period from 850 to 1050 or 1300, so each are 200-year periods, but you can see that the range of sensitivities is very different in each 200-year period. So this 200 period, this 200, this 200, and so on. Remarkably different despite the overlaps among them, and they're all slightly different from the control simulation here. So what am I saying? I'm saying that not only is climate sensitivity itself dependent on the mean climate, which we saw was very different from the last glacial maximum for the interglacial for the current period, and if you go back into paleo records and so on. But climate sensitivity didn't include carbon cycle, and carbon cycle sensitivity to climate change itself is also non-stationary. It's not a fixed number. So how do we get a handle on climate feedbacks then? What evidence can we use? There are some good examples. This we have seen before, the interannual variability of atmospheric CO2 and the temperature anomalies here and the precipitation anomalies here. So in general, other than the volcanic eruption impacts, there is a high correlation between CO2 growth rate in the atmosphere and temperature and precipitation. So that indicates that carbon cycle feedback is related to warming and precipitation changes, obviously, because vegetation response depends on those two as well. And if you remember, again, just to remind you, this interannual variability of CO2 growth rate is derived from the Keeling curve itself by removing the trend and taking time derivative, for example, year-to-year changes. So you can see the volcanoes that we talked about before, Agung, El Chichon, Pinatubo, and so on. And there are El Niños as well, like the 97-98 El Niño, and a relatively quieter, weaker El Niño period with warming happening around the dateline instead of the typical El Niño where the warming happens in the eastern Pacific. So that also affects the distribution of rainfall, what we call the teleconnections of El Niño. So to remind ourselves of the teleconnections, El Niño and La Niña. So El Niño conditions during December, January, February, the boreal winter months have certain warm and cool anomalies, you can see, and dry and wet anomalies. So you can imagine that the vegetation, terrestrial ecosystem, and the ocean are getting hit with temperature anomalies as well as precipitation anomalies, which is bound to affect vegetation and CO2 growth rate, fluxes, and so on. And the teleconnection also depends on the season. So during the boreal summer months, again, the detail is that El Niño actually peaks in December, January, February. That's why it's called El Niño. The Spanish colonizers in the 1800s noticed that warm waters tended to show up once in a while around the coast. Instead of the cold waters, they would get warmth. They enjoyed it, and it came around Christmas. So they called it the Christ child as a gift from God, or El Niño, the boy child, right? So there is a seasonal dependence, and the spatial differences you can see is the anomalies are very different. And La Nina, which is the opposite phase of El Nino, so instead of being anomalously warm in these regions, sea surface temperatures would be anomalously cold in these regions. Obviously we cannot call it anti-El Nino, Antichrist child, so we call it La Nina, a name coined by George Philander from Princeton. And you can see that it's not exactly symmetric. There are some similar responses in the opposite sign, but this one is missing here, and there is some new one here. This is very different, these are different, and well, this is almost symmetric, but some. So La Nina and El Nino are also not symmetric. So depends on how the convection moves, because convection, which is the heat release in the atmosphere, which is a massive amount happening around the western Pacific maritime continent, sends off perturbations to global weather, creating these anomalies, and the way the perturbation happens in El Nino and La Nina are not the same. And again, La Nina teleconnections also have dependence on seasonality. So the point is, of course, that the CO2 carbon cycle feedbacks are happening on El Nino, La Nina timescales. So using models and data and satellite observations of vegetation responses and so on, we can try to get some handle on the carbon cycle sensitivity to climate change, Climate change is a steady long-term change, so it's not exactly the same, but during an El Nino there is like a mini global warming, so it does provide some analog. People also try to see if the seasonal warming that happens as the sun crosses north or away into the southern hemisphere, the temperature changes that happen over the seasons can be used as analogs for climate change in terms of the responses in carbon cycle and other things. Not exact analogs, but many things can be learned if you are careful and combine data with observations. So again, complicated story. Nailing down the feedbacks is very critical, and it's done with the help of El Nino timescale feedbacks, models, paleo data, current data, and so on.